Hello everyone, welcome to this workshop. Today we are going to talk about an integral equation based stiffness formulation for shear deformable plate bending dynamics. I am Nermeen Hesham and let's get started. Our content for today is introduction, main objectives and organization, the proposed dynamic formulation, numerical implementation, numerical examples, conclusions, and recommendations for future work. The dynamic analysis of plates plays an important role in several engineering fields. In many scientific and engineering fields, problems in a given domain are described by partial differential equations together with boundary and initial conditions. Analytical solutions are generally limited to simple cases, but for complex cases, analytical solutions become difficult or impossible to apply. Consequently, numerical methods have become effective tools for obtaining accurate, approximate solutions. Among these, finite element method and boundary element method. Finite element method, sometimes referred to as domain type method, as all the considered domain is needed to be discretized. Boundary element method are a strong alternative to domain type method as they involve boundary only discretization. There are three types of boundary element method: direct method based on a virtual work principle, indirect method based on the classical superposition, and variational formulation. There are many dynamic analysis techniques using boundary element method as static fundamental solution, DRM, time difference technique, direct difference technique as harmonic analysis, time dependent fundamental solution, and Laplace transform. The proposed formulation focus on treating the involved plate as single element. A boundary integral equation method is used to form stiffness and mass matrices for an arbitrary shear deformable plate in bending using innovative technique. Hence, those matrices are used to solve the dynamic equation of motion. This formulation is considered for free and forced vibration. The developed technique involves boundary discretization plus few internal discretization to define mass and measurement points. Several numerical examples are solved to demonstrate the accuracy and the efficiency of the present formulation. To perform the proposed dynamic analysis of plate, it's necessary to extract stiffness and mass matrices using boundary integral equation. This process begins by defining the degree of freedoms inside the plate domain. These degree of freedoms are postulated at least at the loading and the measurement points in case of forced vibration. Whereas in case of free vibrations, these degree of freedoms are postulated at places where certain modes are desirable to be obtained. Despite these facts, other degree of freedoms are sometimes necessary to have a consistent representation of the plate mass. Three ways of postulating degree of freedom are proposed. The overall domain is discretized into cells, or part of the domain is discretized into cells, or defining degree of freedom at small cells or points. This is the used direct boundary integral equation. Noting that at degree of freedom cells, unknown forces will appear, which will later be used to compute the stiffness and mass matrices. Therefore, an additional integral equation could be added by collocating at the center point of each degree of freedoms. It is combined two equations in matrix form to simplify using them. In order to compute the stiffness matrix, matrix form is used with different prescribed virtual displacement cases. Each case involves applying a unit generalized displacement along of one of 3 degrees of freedoms at each cell with no domain loading. By collocating all stiffness cases, matrix form could be written as this. Hence, the stiffness matrix could be computed directly. Mass matrix represents the reactions along degree of freedom when having zero displacement along them, with considering domain loading as on weight only. This outcomes vector which represents the mean diagonal of the required mass matrix. To obtain stiffness and mass matrices which used in equation of motion, a condensation of rotational degree of freedoms is performed. After extracting stiffness and mass matrices, equation of motion could be solved. To perform free vibration analysis, the eigenvalues is computed and then frequencies can be determined. To perform forced vibration analysis, Hubble scheme is used to determine the time history of the vertical displacement at any point at the plate. Based on proposed formulation discussed, a flowchart has been created to illustrate the solution procedure. Initially, extracting stiffness and mass matrices, then condensating rotational degree of freedom. Finally, using equation of motion to perform dynamic analysis. In case of free vibration analysis, eigenvalues is computed, but in case of forced vibration analysis, Hubble scheme is used to extract the displacement curve for any point over time. A series of numerical examples are solved to demonstrate the effectiveness of the present formulation. Example 1, free vibration of rectangular plate was simply supported along its longitudinal edges and is clamped on the transversal edges. The results of this problem are compared with analytical solution, a finite element method, thick plate, or 3D finite element method. It can be seen that the present formulation results demonstrate better than those of the finite element method compared to analytical solution. Example 2, free vibration of rectangular plate was clamped on all edges. Results of the problem are compared with the analytical solution, finite element thick plate, and 3D finite element method. The results obtained from the present formulation are in good agreement with those obtained from analytical solution. This demonstrates that the present formulation remains accurate for both thin and thick plate. Example 3, forced vibration analysis of simply supported plate subjected to heaviside dynamic load uniformly distributed over the entire area of the plate. The results are compared with analytical solutions. It was used 3 meshes, one mesh with full domain discretization and 2 meshes with partial discretization. It can be seen that the results are in excellent agreement with the analytical solutions. Example 4, forced vibration analysis of simply supported plate subjected to heaviside dynamic load uniformly distributed over area 0.4 times 0.4 results are compared with analytical solution. It was used 3 meshes with full domain discretization and another 3 meshes with partial discretization. This results demonstrates good agreement with an analytical solution. Example 5. A reciprocating pump is mounted at the middle of a steel plate clamped along 2 edges, subjected to harmonic force. The results are compared with finite element method. It was used 2 meshes with full domain discretization and 1 mesh with partial discretization. The results from present formulation are very close to the results of finite element method. The former examples demonstrated a verification of the present formulation. In this example, a practical slab is solved and compared results of finite element method. It was used a set of full domain discretization meshes and partial discretization meshes. In case of pre-vibration analysis, the results demonstrate the validity and the efficiency of the present formulation results in comparison with finite element method. But in case of forced vibration analysis, slab is subjected to the dynamic load applied on the hatched area. It's observed that the results from the present formulation are almost identical to finite element method. This is even when only using a few number of points instead of dividing the entire domain. Based on former examples, it concluded the proposed formulation is well suited for analyzing both free and forced vibration. In this formulation, it's not essential to discretize the entire domain into cells. Instead, it's sufficient to use a limited number of points. The results obtained from the present formulation are in good agreement with analytical solutions compared with finite element method. It requires less computational effort while providing higher accuracy than other numerical methods, as accurate results can be achieved without the need for a large number of degrees of freedoms. This formulation is suitable for practical slab structures without requiring huge computational effort. This formulation can be effectively used in other fields, opening up new research areas. For example, dynamic analysis of post-tension slab, walking vibration analysis, automated selection of representative mass points to improve usability and reduce modeling effort. Dynamic analysis of functionally graded and laminated thick plate, analysis of soil structure interaction and fluid structure interaction, incorporation of damping effects onto the dynamic analysis, application in aviation engineering, such as the dynamic analysis of functionally graded wing structure. Thank you.